In starting off this in-service, just let me, give you a basic idea of what we're doing here and why we're doing it and where we're going with it. Now, one of the things that I want to do too is in addition to trying to remedy some of the problems that I've learned about with regard to this kind of a theory, is to draw a distinction also between variance and foundation theory. Foundation theory is something that I've done pretty much all of my academic life. I started this stuff. I can kind of feel it. Right, almost the moment it started. But this was in 1972. Driving up the driveway to Yak Estates in Fairbanks, where I lived there, University of Alaska, Fairbanks. And I had a certain question in mind, and that's kind of where it all started. And the question was that it had to do with why do people behave the way they behave? Why do they do what they do? And that started going on and on and on. And it also has to do with, at the time I was teaching native students, the question was, why are these kids having so many problems, getting through the academic environment, getting through the university, particularly in math and science. And, those kinds of questions that led up to foundation theory. At the same time, I was reading Asimov. I was a graduate student in physics, or geophysics technically, but I was a theoretical physicist, and one of the two at the Geophysical Institute at the time. And, so I was the kind of a person who would approach any question I had about why students can't learn or why people do the things that they do with the eye on a mathematical model, because that's what mathematical physicists do. And so, that came down then to starting to develop brain models. Well, anyway, that was 1972, and then by 2002, it was September of 2002, so now we have something of an anniversary here, because this is September of 2005 now. But in 2002, I started writing what has become known as the Variance proprietary literature. That's chapters 1, 2, and 3. That some of you guys at Dataflow have that, and you've gone through it in some detail, and of course Jerry has it. But there's other writings as well, but those 3 chapters are referred to as the Variance proprietary literature, or VPL. So when I mention VPL, that's what I mean, are those 3 chapters. Okay, foundation theory is primarily a theory about how the biological brain works. And how the biological brain works. Now, keep in mind that if you look through the literature right now today, get on the internet, for example, and put in anything you want with regard to how the brain works, and study it and study it and study it, read everything you can find, and when you get done, what you'll end up with is almost no information at all. You will have found that we don't know how the biological brain works at all. For example, we don't know what memory is, not at all. There are some really neat ideas and stuff out there, but they don't really have any handle on what memory is. Even some of the best brain researchers in the world will tell you that although Stephen Rose, who wrote the book The Makings of Memory, who is one of the premier researchers in England, he wrote a book. It's a very entertaining book about his work in memory, and he says after spending a lifetime trying to figure out what biological memory is, and he did figure out a lot of stuff. Him and Eric Kandel recently won the Nobel Prize doing similar work. Rose says that in thinking about my mother's face, for example, what I did doesn't even begin to explain that. You know, what I've done in my entire life doesn't even touch what's happening as I look into my own mind. And, you know, and it's stuff like that through the years, you know, that has spurred me on, you know, to do the things that I do. Okay, so, you know, we can draw a distinction between foundation theory and variance corporation, but then there's also the problem about, well, what is it that Paul Goodwin does? You know, I sit down there in my cabin, which is kind of on the small side. It's full of electronics and books. That's about all there is in there. You know, except, like, you know, you have a bed and kitchen and stuff like that. But I mean, electronics and books, that's about all there is. I come into Anchorage and stay in hotel rooms. And then I go to Barnes and Noble and I buy books, you know, on the cheap shelf. And they're hardback, you know, and whatever it is that turns me on at the time. And then I read them while I'm in my room. And then I take them back to Kenai and give them to the Kenai library or the Soldado library. So my library in my house, which is fairly large, is all science and technology. It's all heavy stuff. All the rest of it I give to the other libraries. I've given them hundreds of books because I read a lot. Well, what is it that Paul Goodwin does, I hope will come about. You know, you'll start to see some of that with this 2-day seminar. This, by the way, when I used to teach here at Alaska Pacific University, this is where these 2-day seminars or these 2-day in-service things started. Back when this was Alaska Methodist University, it went belly up and closed for a while. And then about I don't remember the years. I don't quite remember the year, but anyway, 68, 70, something like that. They called in Glenn Olds from Kent State. He was dean or president or whatever they call these people in universities. You know, the head of Kent State, anyway, during the Kent State shootings, and brought Kent State out of that mess. Anyway, they brought him up here to reopen Alaska Methodist University, and then opened that as Alaska Pacific University. And I was president of Earth Science Consulting Technology at the time, and vice president Chalissa, building the Sheraton Hotel and all that kind of stuff at the time. And Glenn Olds came to me, and I started teaching here in philosophy here at APU way back when. Just when it just opened, and I did that for free, of course, because APU sure didn't have any money. You know, it didn't for many years, even though they have a huge land endowment. Anyway, those things started with Glenn Olds and the idea of going to various rural school districts and teaching this same course, you know, to rural school teachers to help them keep up with their recency credits. Okay, those things, you know, this is foundation theory doing this. And the reason I mention that is because, remember, this is foundation theory. And the way you check a theory scientifically is you compare it against what is real, what is really out there in the objective world. And so when you can apply a theory to a whole host of different subjects, then you start to get the feeling, oh God, I'm really onto something here, because it explains kind of anything you want it to explain. And in this particular case, you know, foundation theory started off as an educational theory with a real strong educational bent. and came to the same conclusions. For example, that Judy Kleinfeld, I wrote a paper a long time ago, about that, and it came to the same conclusions Judy Kleinfeld came to with regard to students who were boarded out to these schools as I was, when they're real young, and the psychological overlay that puts on a human being. Okay, later on, and I mentioned in an email, that I worked for the cops here in Anchorage for a few years, and I did, and the reason, they want to know stuff like, well, how come a person is a pedophile, for example? That's a hard one for most people to understand. What the hell is it that motivates pedophiles? And so, or mass murderers, and you try to explain that to them. But the beauty of it was foundation theory did explain it to them. They had a handle on what exactly was going on. Okay, now, this particular in-service is going to take a different bend. It's going to take a bend toward electronics. And that means that it's going to take a bend toward what Variance Corporation is all about. Now, or what I had originally envisioned with regard to Variance Corporation. And I think that it'll probably still end up being that way, because I don't know that I had a particular image of how that should go, but it's certainly a general image of it. Now, and then hopefully, through all of this, you'll also gain some understanding of what it is that I do, and where this is going, and that's important. One of the things that I did learn in the last year and a half, 2 years, we had a couple of lawyers, involved with Variance Corporation. One was based in Houston, one was based here in Anchorage, and they were high-powered attorneys. Particularly Gerard down there in Houston. He had a lot of contacts in the telecom industry. Okay, so this was being sold across the board in the telecom industry real heavily, because Gerard represented those people in their own patent disputes, because he's a patent litigation attorney. And so he knew the people, but then going out there and trying to sell this to them, there was some real problems. And of course, one of the problems was a prototype. We didn't have a prototype to show them something, that, okay, here, you turn this knob and it works, or whatever it's supposed to do. So that was a problem. Now that's going to be the culmination, so to speak, of what this in-service is. But in the meantime, I still need to be able to impart to all of you the meaning of what foundation theory is and where this is going to go. Because this is going to go a long way. To make a long story short, what I'm after is consciousness. I don't know if I'll live to see that, but long enough to see that. But that's where I'm going with this. And there's already in foundation theory a lot of real good indications as how to open that door. Although foundation theory at this stage of the game, at this point of development, does not involve mind, and it doesn't involve consciousness. It involves the brain, how a biological brain works. Now, a little bit later on, tomorrow, I'll editorialize on mind and consciousness, but for now, it's just how the biological brain works. Some interesting things that you should know is that long before you consciously take credit for something that you've done, your brain already did it for you. You have only become consciously aware of it and then somehow convince yourself that you did it. You didn't do it as a self, as the thing that you call me didn't do it, your brain did. And it did it without your conscious intent or your conscious recognition of the fact that it was being done. It got done anyway. It's only later that you come about a tenth of a second later that you become aware of it, and then you take credit for it, having consciously done it. It is things like that that cause psychologists to wonder if things like free will are just so much, if it even exists, things like free will. And I have that question as a serious question. Are there things like free will? Well, I think there is, but I mean, there is still that question. Because again, you have things going on in your brain that are really interesting, and that, your brain does, not that you do. And that's what we're not going to deal with quite yet. Later on tomorrow, we'll start dealing again with mind and consciousness. And I hope you all read this Life in Hell cartoon. It's pretty interesting. I wanted to give that to Jim, particularly Jim Godstein, because he runs Psych Rights, Psychiatric Rights Inc., and helps a lot of people get out from under forced drug therapies and that sort of stuff. So, the idea that this thing deals with Prozac is pretty good. Now, it turns out, though, Prozac really does work for a lot of people. And so do a lot of the other things. Well, let me get started on foundation theory then. Oh, and one other thing, by the way. I'm going to be, this is just a mechanical thing. I'm going to run this thing kind of like regular college classes, which is to say 45, 50 minutes a stretch. And then we quit for 5, 10 minutes. Yeah, the reason for that is that universities have been going since the 11th century. We've got a lot of experience, professors in colleges have got a lot of experience on how long students can run and how long they as teachers can run. And it comes out to about 45, 50 minutes at a crack. That's about, and Jerry knows more about this than I do, but that's about the limit of a person's attention span. And then as far as me is concerned, the teacher, I'm using up the neurochemical resources like there's no tomorrow doing in-service training. And I'm using them up fast. And you have to give yourself a break. Otherwise, if I don't, I'll start getting into this in-service further. I'll start battling. That won't be making any sense.
How would we tell the difference? Sorry, it was such a clean shot I had to say.
No, I mean, a person waits all their life for a chance like that.
Fortunately, you won't fail the class for that comment.
Yeah.
I see.
So anyway, I'll kind of do it on a 45, 50-minute basis, just because it works. And so, I brought my little clock with me here. So anyway, let me get started on the stuff and that. And where we start in foundation theory is to get a philosophical basis for where all this begins. And there always has to be that philosophical basis because that's where everything starts, in the philosophy. What I'm going to be doing here is something that's going to be familiar to Barbara, because we've talked about it before when her and I were a student teacher, that kind of thing. And what I would do is call your attention to this particular package here with a cartoon on it. The second page in. I had, by the way, this particular figure came from here in APU. I was teaching a graduate neuropsychology course for 13 years here at APU. And that particular course is when I was teaching that, when I came up with this particular diagram. I'll probably recreate the diagram on I've got Corel Draw now, you know, they didn't have any such thing back in those days. So I could do this on there and do a little bit better job, but this is a real old diagram. But what it gets to is this. So we have what we have here is one of the reasons that I draw diagrams and give them out like this is because I don't draw too well, because my hands shake a little bit and all that sort of stuff. But we have an objective universe, as you can see. This is the thing where this pencil here that I'm drawing with, and then a perceptual and a conceptual universe. And I just we'll call that reality, perceptual reality, and conceptual reality. Now the objective universe, consider what that is for a minute. As a physicist, what do? I go out there and I make observations, and I try to make observations such that I can quantify it, you know, and I can rationalize it. And so when I do that, I tend to make mathematical models of it. Okay, and then the mathematical model becomes the reality itself. The mathematical model exists out in here, whereas the reality exists out here. I'm going to have something to say about that in a minute. Now, one of the things that I did in this particular course, you know, when I was teaching this, was that I was pointing out that the perceptual reality, you know, has a window in it, and that's the window that you are open to when you open your eyes and you observe. Interestingly enough, when people open their eyes and start to observe these kinds of things, whatever's out there, most of the stuff that they observe, they don't see. There's a lot of things out there they just don't see. They cannot comprehend it. And this is part of the problem with the telecom people. We have a product, you know, that will quantize frequencies down to fractions of one cycle. I mean, it will quantize it ridiculously small. And I didn't bring any of those quantization diagrams with me, but I can send them to you by email. I have them on my computer here and there. But can get things really small and yet no one would believe any of it. Okay, you know, so you know, it's sitting there, even though they're sitting there with a patent, you know, being able to see it and look at it, they can't quite grasp or accommodate in their head somehow. They can't quite get it, in other words, what's going on there. Well, what I had done was I had said that, well, that happens in a lot of different ways. And what I had done anyway is said, well, increase this particular window that you have on reality. And that is what I hope that education does for everybody, and I think that it's true that it does. Once you have an object in reality, and that's what those, in this particular case, ovoids and other geometric figures, you perceive those in perceptual reality. You transmit them into the conceptual domain, and you form concepts about them. Okay, so that there's a difference between the objective reality and the conceptual reality, as is filtered here in the perceptual. And again, Jerry has more information about that from his field, one of his fields, which is neurolinguistics. You know, and those guys deal with perceptual realities quite a bit. Okay, now, I wanted to do this because if we've got a situation like this, in a philosophical sense, we've got to start figuring out what it is that's out here and what it is that's in here. Now, what we're going to be doing in here, though, is we're going to take this same basic idea And I'm going to be looking at something like this, where this is the perceptual interface here. And then this one here is the behavioral interface. And we're going to be looking at what's going on in here, in between those two interfaces. Now, what does that mean, perceptual and behavioral interfaces? Well, Jerry just was, we were walking in the door, said, I can tell that you can hear better by virtue of your own voice. You know, because I'm not talking so loud today. And I had to yesterday because I couldn't hear myself. I couldn't quite hear myself normally, so I talked louder. And so now I can talk softer, and when I'm more normal, sometimes you can't hear me. I talk real softly.
You do.
So maybe not hearing it is a good deal for you guys. Now we'll be getting into this part of it anyway. The idea, just to give you a context for this, is that the perceptual and behavioral interface and what's inside of here, behaviorism, which came on the scene in the early 20th century, you know, in that zone, in that region, you know, started ruling the roost in psychology for 50, 60 years until about the 1960s, and was really heavily favored in the whole psychological world. The basic idea behind behavioral psychology is that you have a perceptual interface and a behavioral interface, and it didn't really make any difference what was going on here, because here, if you had a stimulus, here you'd have a response, and that's all that mattered. A given stimulus and a given response, and what went on in here didn't matter. And that ruled the roost, again, for 50, 60 years. But what it did was it caused this huge number of psychologists to not even worry about what's going on in here, which is to say this part, this perceptual reality part, and also this part. Okay, they just didn't care about that. Okay, but fortunately, you know, there were a number of psychologists at the time doing work that did care about what was going on in this black box right here. And they started writing their ideas down, and some of those ideas we will be using in here during this in-service. Okay, now what we will be doing in our case is we will look at a stimulus here, and we will also look at a response here, but in our case we care about what's going on in here. That's where we're going to be that's what we're going to be looking at primarily, is what's going on in that black box. Okay, once we have an understanding roughly of what's going on inside of that back box in a neurological sense, then I think you'll find that what we can do is we can start reifying those things in a different medium. We don't really need to use neurons and synapses and neurochemicals and all that stuff. We can use a different medium, and the medium would be electronics. And there's some reasons why you can do that that's related to this particular diagram. What I'm going to suggest to you in this particular case is this, and this is kind of important in a philosophical sense, but it's kind of important. Actually, it's profoundly important, this particular observation, and I don't know that I've ever seen it before. I certainly have never read it before. But in this particular area here of objective reality, let me suggest to you this, and I'll tell you the reasons why I feel that this is the case. Let me suggest to you this objective reality that you see around you. The trees, everything around here, us, you know, that sort of thing. What all of that is a precipitation around a mathematical framework. In other words, this OR right here is actually the mathematical universe, okay, the real mathematical universe, not the ones that the mathematicians have dreamed of. Okay, this is the real mathematical universe. Now consider that like, for example, the grass out there, or any lawn, the grass on any lawn, and in the morning, the dew precipitates on the grass. The dew doesn't precipitate anywhere. It precipitates on the surface of the blades of grass. There's a logic to it, a rule to it. It will precipitate on the leaves of the trees or whatever. But again, there's a framework on which the dew will form. It literally precipitates. Using that as a metaphor for reality, then what we can say then with this particular philosophical positing I'm doing is that all of this, including us, we precipitate around a mathematical framework. That is this OR. That is what objective reality is. Okay, now, again, we always have to make the distinction that there's a difference between this mathematical universe and the one that the mathematicians dream of here. And that's a fairly easy thing to see. Mathematicians say this. Okay, so then if x equals 2, okay, therefore y equals 2. Okay, and you'll notice what that is an assignation. It's just an assignation. It does, now the point is that does that exist? That exists in this mathematical universe here in the conceptual reality, but does it exist here? Okay, now let me take this one step further now. When a physicist, a mathematical physicist says this, and let's do this, y equals f of x. If a mathematical physicist says that, this is no longer an assignation. This means to a physicist the same thing as, literally the same thing as. And then that's how they can make the translation between that, whatever it is observed out there, and the modeling that they're trying to do. Okay, so this is no longer, for a physicist anyway, this is no longer an assignation. It is now the same thing as. And because of, the easiest way to imagine it is through quantum mechanics, back down to the basic reality of things, the basic stuff of it all. Well, that's exactly what the situation that's going on. And what's going on also in quantum mechanics is that f of x can be anything you want it to be, provided it works. Okay, and that's what quantum mechanics is. Okay. It's just a bunch of equations that work. There is no theory for quantum mechanics. There are suggested interpretations, like the Copenhagen interpretation, the many worlds theory, that kind of thing. But there is no theory that goes with it. Okay, now the reason that making a suggestion like this is the mathematical universe, as opposed to simply matter, is really at its most fundamental level something like a mathematical framework. To make that assertion is important because now you can start putting a theory behind, quantum mechanics. There can actually be a theory. And then now there's something other real important, you know, and I'm just doing kind of an overview of foundation theory. There's something important also for us in this. And that is that if this is reality, objective reality is in fact the mathematical universe, the real mathematical universe, as opposed to the conceptual mathematical universe. Remember, the conceptual mathematical universe are liable to contain elements that aren't found here. You know, like Cantor dust. Does that exist out here? Well, in a sense it does. And then this gets to be a philosophically difficult problem. But, you know, we just need to recognize that this is liable to contain more stuff than this does. Because every wave equation doesn't work in quantum mechanics. Only those wave equations do, only particular ones like Schrodinger's equation. You know, not every wave equation works. If we take that approach, okay, now this also has another profound implication. There are 4 foundational pillars of physics. You know, quantum mechanics and relativity, and then there's thermodynamics and kinetic theory. Those 4 foundational pillars philosophically don't match one another at all. You know, now you can get kinetic theory and thermodynamics to match, provided on the kinetic theory part, which again is a mathematical model, provided you put the restriction on it that you have to have a range or limit to the initial conditions. Now, mathematicians can't live with that. You know, they'd rather shoot themselves than to live with the idea that you have to restrain or restrict, you know, things like initial conditions. It should be cleaner than that. It should apply to anytime, anywhere, any way. Okay, but in reality, if this is in fact the mathematical universe, the objective universe, the thing that we've been calling the objective universe, and then now let's look at the cosmos, let's call that the objective universe. If that's the objective universe, then it does have initial conditions. You know, now, for lack of better words, there was the Big Bang and creation, and that is all there is. There isn't anything outside of that bubble. It's just the bubble that we're on. We live on the skin of a bubble that's expanding. That's our universe, and that's all there is. There are initial conditions. Okay, so just by virtue of that one philosophical principle, if you can get people to believe it or accept it, that this is in fact not a matter of objects and matter, it's more a matter of mathematical framework on which matter and objects precipitate, just as the morning dew does on the blades of grass out there. And they evaporate later on too, as we will, as our objective universe will. Okay, so if this is a mathematical framework, and we accept that this may have elements in it that are not in the real world, okay, then that does some other things for us. Okay, there was a PhD research level, you know, paper writing professor there in England who came out with a notion, this was a couple of years ago now, who came out with the notion that consciousness is the mathematical envelope, the electromagnetic, mathematically defined envelope that surrounds the operation of our brain. And that's what consciousness is. At the same time, a graduate student in Australia, you know, neurobiology or whatever she was working in, or mathematical physics, whatever. She came up with the same notion in the paper that she wrote. So those two were coincident. And I read about that, you know, and I tried, you know, tracking down this stuff as much as I could. And it was something that, anyway, I could really believe in. You know, that is what consciousness is. It's that mathematical envelope. Now, if we accept that OR, you know, the objective world, the world of these things, or atoms, or, you know, particles and billiard balls and that sort of stuff, that is, in fact, there's something deeper, a mathematical framework around which things like this precipitate, again, just as the dew drops on the blades of grass. Okay, then, now we've got a doorway into consciousness. Okay, because consciousness, too, is something that is real. You know, Voltaire said, I think, therefore I am. Well, we can all do that. On the other hand, all of us can sit here with our respective consciousnesses, looking at each other, and I don't know if you guys are conscious at all. I have no idea. I can presume that you are. I can conclude that you are. You know, surmise that you are. But I don't know that you are. But I know that I am. Is that real? Is consciousness real? Well, see, there's the problem. If you think nobody knows anything about how the brain works, you ought to see what they know about consciousness, which is absolutely nothing. There's a lot of books written about it. I tried reading them all, and there's still absolutely nothing. There is no reasonable doorway into what consciousness is until these two people came along, a graduate student and a researcher, you know, completely independent of one another, and thought of this idea. Okay, and then that was another thing that spurred me on to begin concluding that, okay, this is not really an object, matter-oriented universe. It really doesn't have much to do with objects and matter. What it has to do with is, it has to do with the mathematical framework, and so let's go discover that. Okay, one of the reasons why I call this foundation theory is because in Isaac Asimov's original Foundation trilogy, you know, which I had read by the time Foundation theory was being developed, he had talked about, you know, in the books, his primary protagonist is Harry Seldon, who had developed the so-called psychohistorical equations. And from these psychohistorical equations, he could apply them to the benefit of mankind. Okay, the idea being that the galactic empire was crumbling, and there would be a long interregnum that could be very much shortened using these psychohistorical equations and causing events. Because if you have a mathematical model, you can do predictions. You know, like if you're building an airplane, for example, you know, and your mathematical model says, well, hell, this isn't going to work. Well, probably won't. You know, your plane will probably crash if your model says that it will. So you don't build that plane. You build it a different way. The way your model says that it will work, you fly it, and the damn thing does work. Yeah, after a while, you start believing, well, shoot, this stuff has something to it here. You know, which is why we have all the stuff that we have now. Somebody is believing it. You know, we're really into this mathematical model stuff. But again, nobody that I've ever read has said that's what this is. Okay, now, just a second here. One of the things that we have then, anyway, by assuming this, again, this new assertion that object-related reality is actually a mathematical universe, is actually the mathematical universe, is we have a handle on now the problem between two of the foundational pillars, which are, is statistics, the statistical kinetic theory, and then also the thermodynamics. We can reconcile those using this assertion. But we can also reconcile relativity and quantum mechanics, which we'll get to as we go along, because the answer to that problem turns out is in how the brain works. Let's take a break. In most cases, it's just a leg, and you touch a nerve ending, and you'll see the thing joint. Okay, and so you make the conclusion that, well, something electrical is going on here, and you keep doing your experiments and keep doing your experiments, and then you keep learning more and more and more. Okay, you keep doing a lot of looking, a lot of observing. So what we have finally then is we have people like KL, and if you turn in this particular packet that has a brain of PET scans. Oh, now, that's something I should mention as well. These particular figures are directly out of BPL. And they're in order as they appear in BPL, so the figure numbers are kind of like the page numbers. Okay, so if you look at figure 2.4.
It's the second packet starts with colored.
Yeah, that packet right there. Yeah. Okay, and if you go to 2.4, which would be page 4. And then look at that particular drawing. Now this is after KL. KL, lived over a century ago, and he started coming up with these drawings of his that were based on a Golgi-stained thin slice of tissue, nervous tissue. Okay, now the interesting thing about nerve tissue is, with a Golgi stain, is that Golgi stains only stain a certain small percentage of the neurons and the wiring that goes with the neuron. It only stains a certain small percentage of it. Now, I don't, when I first started studying this stuff, they didn't know why that was the case. It's just that's what happened. It just stained only a certain amount of it. Since then, they've come up with a lot of other stains, but the Golgi stains were really good because you could look at individual neurons. Since it only stained a few of them anyway, small percentage, you could actually stain a sample of tissue which may have a jillion neurons in it, but only a few of them would be visible. Okay, so KL did that, and came up with drawings like this. This particular thing is a Purkinje cell, it's called. It's one of the neurons in your brain, prevalent in your brain. There's a lot of those Purkinje cells in there. and as it turns out, you can see that just from what KL did with his drawings, again, over a century ago, that there's a lot of wires associated with one lousy neuron. There's a lot of wires. Now, keep in mind, this is only two-dimensional. This is made from a thin slice. Okay, now if you rotate that, through 360 degrees, man, that's a horde of wires. That looks like a ball of cotton candy, or worse. It's even worse than that. Nowadays, we can get a graduate student and have them count the damn wires. And so it turns out there's about 80,000 wires associated with a Purkinje cell. So 80,000 connections.
Question, that was 80,000 that showed up. It's calculated from the stain. In other words, that's what showed up, or what was actually there?
Pardon?
Oh, I'm sorry, 80,000 in terms of what showed up, or what was actually there?
What was actually there? Yeah, typically neurons, I'll get into that here in a minute, but typically neurons have a lot of connections. I always use, and many other people do, 10 to the 3 connections per neuron. But it's more like 10 to the 4, 10 to the 5 in that range, which is where 80,000 would lie. Okay, now, given that, we have these people doing this kind of work, given that they've known about, the galvanic response of frog legs for a long time, they were able to do things like trace the galvanic response back, to let's say the body of the frog. In certain areas in the body of the frog, it allowed the leg to move, but certain areas wouldn't. So anyway, this brought them to, after a long lot of experimentation and so on and so forth, this brought us to a point where we knew that the nervous system in a frog, for example, wasn't a continuous sort of a thing like you would expect to see in a radio, for example. Well, radios aren't continuous either, but it isn't a continuous wire that goes from one point to another. Rather, somewhere in this deal there was some breaks, so that they were aware of the fact that neurons don't connect directly to one another as you would expect in a soldered joint, for example. Rather, there was some sort of gap in between neurons. Okay, now, back in the day of Kayal, they sure couldn't see those things. Okay, nowadays we can, because nowadays we have scanning electron microscopes. And most of the the micrographs that you see of neurons and the synapses are scanning electron microscopes. That's how small these things are. And now, fortunately, there are other animals, however, that have nervous systems that are very much cruder than taking a thin slice of a human brain. You can get frogs, for example, which are much, much simpler, their nervous system is, than ours is. Okay, so that people started discovering things, particularly in the ocean, that are real simple. And for example, an Aplysius snail became the real favorite because it's a real big thing, it's got real big neurons, you can see them, you can see them with your bare eyes, and they're so big. And so you can very handily experiment on these creatures. Okay, so they became the favorite topic. And as a matter of fact, that's where Candell did his original work on Aplysius snails and came up with what became known as Aplysia memory. And that's what Candell won his Nobel Prize for, doing that kind of research. Okay, now, in any event, a long time ago, they had known that neurons were complicated, very complicated, and they knew that they weren't directly connected to one another. They were connected in a sense that there was a gap there. So they've known about the idea of the synapses for a long time. But it took a long time, to get to a point where they could actually see them and experimental methods being developed so that they could actually ascertain that there was a gap there. Okay, those gaps became known as synapses anyway. And so what we have then is a situation like this, and I'm going to idealize this. If you look at figure 2.4 and you just pick out any one wire of that, in that figure, any one wire of that figure, then what we're going to have is a connection. Remember, each one of those wires connects to a different neuron. It will connect to a different neuron. So that the Purkinje cell, which has roughly 80,000 connections per neuron, will connect to 80,000 other neurons. Now, I'm not a biologist, But there is a principle in biology, that you can call, that I call anyway, biological identity. And that is, one cell will connect to another cell, and this connection is just a gap, as we're going to see here in a minute, but it connects to it biochemically, and then the two cells form an identity. That cell knows, cell 1 knows that cell 2 has been connected to it. And so it doesn't have another wire go to it. It avoids that cell because it's part of itself. That would be like connecting to itself. It knows itself. Now cell 2 is itself. Okay, now cell 1 will grow to another neuron. So in general, all of those 80,000 wires will connect to a different neuron. And again, biologically, I don't know that that's all really well known, other than to say, how that occurs, other than to say that biology has that ability for for biological identity. And that allows that to happen. Now, one of the ways that these things connect is like this. And I hope I can draw this halfway decent. I have a G3 computer, which I don't use anymore. It's in storage, but on that hard drive, I have these figures, and I usually just don't have time to transfer these kinds of things to my newer computers, but I would have made, otherwise I would have made a thing instead of trying to draw this thing. Okay, this is the end of one of those wires on that figure 4, 2.4. That's what one of the ends of one of those wires looks like. It's like this. These are often referred to as buttons, these things, same here. This part is the axonal process. That's what that's officially called. The easier way to do that is just say axonal wire. Okay, the reason for that is that because this comes out of the axon of the nerve cell. Okay, now if you look at figure 2.4, you will notice that you have the cell bodies, and you have the axons, and then you have the dendrites. Okay, now the axon, which is going down in this figure, what that does is it projects to another part of the brain and branches out into a tree like this again, over here now. Okay, so there's a tree here and a tree here. This happens to be a dendritic tree. Okay, that, it turns out, is this part. Okay, so this is the axonal. I just call these things wires. And then this is the dendritic side. And that's just usually referred to as a dendrite, which is the way this figure refers to it. Keep in mind that because of this kind of structure, remember now, looking at this figure, this is the dendritic side, this is the axonal side, so there's another flowering like this. That what that starts to resemble very closely is, for example, one of these shrubs out here, particularly a shrub, or a tree, like a birch tree. Up on, you've got a long trunk, and up here you've got all kinds of branching and leafing and everything else. But then it goes down, a long trunk, and it goes down into the ground, and then it also spreads out, kind of like the same as the top of the tree. Okay, as a result of that, what that ended up being called then, this part here and this part here, is arborization. Okay, and that's the reason for that word. And then keep in mind that we're dealing with different neurons in different parts of the brain and the body. And so what we're looking at is arborization, that is different in different parts of the brain and body. And we'll get into a little bit more of that in a minute, particularly insofar as children are concerned. Why is it that kids can't keep their damn milk upright instead of spilling it all the time? Especially if you have glasses like this. Well, we'll look at that. Okay, anyway, you have each one of the axonal wires. Axonal wires, by the way, is outgoing. That's outgoing signals. And dendritic are incoming. Dendritic go to the cell body. And I should probably draw that here. Let's see, how am I going to do this? These are incoming to the cell. Okay, so those are the axonal wires from another neuron. They come into the cell fires, and it goes out the axonal wires down here, this being the axon. Okay, now we're looking here at axonal wires, and then the receiver, which is the dendrites. Yeah, there's a word for that I'll remember in a minute, but I can't quite remember what the two words are for those particular processes. But in any event, I'll remember it in a while. What happens is these axonal wires, when they fire a signal, that's what we're going to look at next. When this thing fires, when a nerve cell fires here, how does the information from this wire get to over here? That's the question in neurobiology. And that was a question that, by the way, wasn't really answered for a long time, simply because the technology didn't exist to really adequately answer that question. It just didn't, the technology just wasn't there. And then the experimental abilities weren't there either. You had to have kind of a renaissance in education, in higher education, before a lot of this stuff could occur. No time in history have we ever had so many college students, for example. We've got a lot of them now, and a lot of them go on to their graduate studies. And so now we're doing things like doubling our knowledge of this stuff every several months. It's just ridiculous. Brain research is just ridiculous trying to keep up with that. Anyway, a neuron fires, and we know that the thing is electrical. And then how does it get to the other neuron, given that we know that there's also a gap in there? And given that we know that when a neuron fires, it is electrical. Okay, so what we can measure anyway, now this will require another figure. What we can measure is this. And this has been able to be measured for quite a while. And this is the last page on that same packet. And that's this firing diagram. Yeah, that diagram can be measured and has been able to be measured for quite some time. Now the reason that's true is because if you look at that diagram, look at the membrane potential in millivolts. Well, shoot, that's getting up there, 40 millivolts plus 40, from about a rest area of a minus 60, there's a pretty good chunk of millivolts there. That's fairly easy to measure, and it has been easy to measure for a long time. So they've known about this ability to fire, and they've known about the electrical character of the neuron. They didn't know for a long time how it was that those particular those impulses were created, nor did they know even longer, for a longer period of time, how this thing worked. Okay, now the reason I wanted to put this particular drawing in here is to examine how it is that these wires transmit an impulse down. And this is an important consideration because, to understand this particular consideration, because it goes to what we can do with this in terms of reifying it later in electronics. You know, this is telling us something. Okay, in a wire, and I'm going to just take a cross section just like is drawn in that figure, like this. And in a wire, what we have is a tubular looking affair, and it's just a tube. It's hollow in the middle. It's full of spinal fluid, if you will. On the outside is the same thing, cerebrospinal fluid. Okay, now this particular tube, again, is, you know, like if you look at a Plesia snail, a neuron in a Plesia snail, and some of its main artery, or some of its main neurons, they're very large, and you can actually see that, you know, they're tubular, they're tube-like. As a matter of fact, we have some neurons like that. You know, the neurons in our arm, for example, are kind of like spaghetti. You know, you could, if you took it out, you know, you could get it out. It'd be about a meter long, you know, and you could pile it up in your hand, you know, and there'd be your neuron. It's fairly large. Anyway, it's a tubular thing, and obviously, if it's a biological device, you know, obviously this tube is going to be made out of molecules, protein molecules, a lot of different protein molecules, and as you probably know, protein molecules are complex molecules. They're very complex affairs, okay? And that's what the cell wall is made out of. Now, as it turns out, those cell walls and the molecules that are in them are referred to, many of the cells are referred to as, in this particular case, voltage-activated gates. And that's kind of a general colloquial term for them, you know, voltage-activated gates. What happens is, and I'm just going to draw in 3 of them, and you can still, when I'm drawing here, you can still look at your diagram there. What happens is if there is an electric field that gets near this thing, okay, there's an electric field that gets near this thing, it will cause that voltage activated gate, you know, open, and consider it, the metaphor for that is usually something like a camera shutter. Only, of course, much faster, but like a camera shutter. And what happens at that point is there's an inflow and outflow of ions, and it's indicated on this particular picture, of ions, you know, again, moving in and out, and they're usually, you know, like potassium and sodium, for example, and one of them is more positive than the other, or alternatively more negative than the other. And what happens because of that gate opening and closing is there becomes a difference in potential between here, this inside here, and outside here, there's a difference in potential. And so what does that do if you've got your voltmeter handy? Well, you know, it causes a spike right there. Okay, now, if a voltage spike is right there, what does that do? That creates an electric field, okay, which then affects that. This one then opens and closes. In the meantime, this one has died out. Now the signal is here. Remember, this is already gone. Now this one causes an electric field disturbance, which affects this voltage activated gate, which causes that to open and close. And so now the signal moves down here. And again, the same process of causing one side as opposed to the other to be more or less positive. Now the question is, well, that's pretty nifty, you know, but how does these things get started? How does this process get started? Well, that's what we'll find out over here. But look at what's going on here, is that we have, you know, what, at least in my own head anyway, you know, I call in situ creation of these nerve impulses. And so what's happening is they appear here, then here, 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 and it's just in situ creation. In other words, there's no current going down here. There's no current going down those wires. What's going down those wires are voltage, I guess, if you want to call it, you know, field effects. There's no current. Okay, this is one of the reasons why the brain is so efficient. Is it can be, you know, these things can work without having to have real high current and power consumption demands placed on them. Now, that doesn't mean we don't burn up power. Obviously, we do. Our brains, for example, you know, in our resting state, you know, burn up about 75 to 100 watts, just sitting there working, you know, our brains, you know, all the time. And by the way, your brain, all of it works all the time. There is no, you only use 10% of your brain. All of your brain works all the time. It may not be working very hard, but it's working.
Now, you may not know this.
Yeah, and then the other problem though is to open that window, your perceptual window, and then opening your conceptual window. That's the hard part, and that's one of the problems that we ran into with the lawyers. That's one of the problems they had. Is that how do you get these people to believe any of this stuff? Well, you can't do a damn in-service like this. Every sales job, you know, I mean, dude, this is too much, and, you know, and you know, and are those people going to be convinced after that? Well, most of them won't be. Most of them may not be. The graduate courses that I taught here, there was only a very small percentage who really understood, but there is that small percentage who really understood and really, really got to be able to do something with it. and it does work. And so it's a question of conceptual and perceptual windows, opening and closing. Anyway, getting back to this, no power is used up because no current is moving. It's just the in situ creation each way along the way that results in something like this, an impulse like this, which is easily measurable. You know, nowadays you can go down to the grocery store and buy voltmeters that can measure this easily. And they've had that ability to measure this for a long time. So that while this thing has arrows on it, again, keep in mind that this is not continuous. This is here and here, and protein molecules, from our point of view, from our eyeball's point of view, are really, really small. But from a micro point of view, they're really, really large. So that what we're having going on here is a quantization in time anyway, in situ creation. Because it appears, the next appears, just like that, just like a movie. Okay, there's nothing continuous about it, it's a movie.
There is, however, some current flow in and out through those gates, isn't there?
Pardon?
Is there a current flow through the gates?
Yes.
But very small.
Yes. Well, it's wait a minute, yeah, it's not quite very small. These things here, when current flows back and forth like this through these gates, what that does is it sets up, and because of these, voltage patterns like this, what happens is that it creates an electromagnetic wave. You can see that. I mean, any moving current is going to do that. Okay, so with these things, when that happens, when these things fire, those are called quantum microwaves. Okay, and remember, again, and they're called, that's what they're called, quantum microwaves, and they they go from here to here to here in situ creation. So you've got these bursts, like a movie of quantum microwaves. Okay, those quantum microwaves that you see, or that you can surmise is there, is what you see when you go in and have an EKG. You go in and have your brain looked at, brain waves. That's what you're looking at, is the quantum microwaves. And you're looking at the quantum microwaves not because they drilled a hole in your head, and stuck probes in there, but they've got a transducer here sitting on your skin. But in fact, those quantum microwaves and the electromagnetic envelope of you as a neural entity is out here somewhere. It goes way beyond you. Okay, so that when you start thinking about the people back in the 60s who, there's a lot of the flower children who could see colors on you, etc. Well, okay, fine. You can see what color I am. The aura. They can see my aura, or they can see somebody else's aura. Well, I don't. Okay, that's fine. You can do that. But the problem is, I can't just dismiss that. I mean, maybe they can. I don't know. I can't see anybody here's aura. I mean, I can't. But maybe they can, because it certainly is there. I mean, in any objective sense of the word, you can certainly measure it. They certainly do all the time, by virtue of those transducers. When I go into, the doctor, for this ear thing, you'll hook me up with stuff, and do nystagmus tests. That's not because he goes in and, sticks a needle in my eyeball to make sure it's not moving or something. He's checking it out with all these sensors, which are a long way away from those nerves that control the eyeball. But the way that's done are these quantum microwaves. Okay, that's the voltage activated gates. Okay, now this is along a wire, and all these things are just these big complex protein molecules that this whole structure is composed of, and that forms that hollow spaghetti-like tube. Okay, and again, that kind of thing ends right here. Okay, and this is the way information goes, is this way. Okay, this dendrite can be thought of as, let's say, on one of these wires. Okay, now that's this wire here. Okay, so these are voltage activated gates. And they are all over the place. They're three-dimensionally all over that wire. So that what you get, these quantum microwaves, is a very, very close together. I mean, almost like at the quantum level, and literally, which is why they call them quantum microwaves. Okay, now how does this process get started? You know, how does that get started? And that gets started here. As a signal is moving down, and in the modern world we can call it information, an information signal is moving down here, this way, in this direction. What's happening up here are things like this. Now, these things here are little, they're called vesicles, and they're little things like puffballs that we find out in the woods here in Alaska. Little puffball affairs. And they are full of other molecules. Okay, now those other molecules, there's about 10 to 20,000 of them in those vesicles. And as the informational packet, which is to say, these things, by the way, are often referred to as nerve spikes. Okay, these waveforms. Okay, as a nerve spike moves down that tube, it pushes those vesicles down along with it, and then finally, when it gets to this face right here, it joins with the protein molecules that are there and spills all of that stuff out into this brain fluid, this cerebrospinal fluid that all of this stuff is immersed in. It just spills it out into there. Okay. Now that, I am drawing it like this, and that's roughly the way it is. It's just one after the other coming in and moving down, dumping as the signal goes, you know, as the informational signal is going along, finally comes to the end, and this is what happens. Okay, and it starts dumping those molecules. Now those molecules are then the so-called neurochemical transmitters. Okay, so that's what these are. Okay, the neurochemical transmitters. Okay, now on this side of this particular gap here, what we have now, what nature has provided now, are what's called, in this case, chemically activated gates. Okay, not voltage activated gates, but chemically activated gates. And what is a chemically activated gate? Well, a chemically activated gate does this. It doesn't care about the voltage, between the two things, between the ends. All it cares about is the chemical constituency. Now, what does that mean? Well, what it means is that these particular neurochemicals here fit into keyholes, if you will. That's the metaphor that's usually used. These things fit into a keyhole in these gates, and they open it, and then that causes that to open and close like a camera shutter again. Okay, same action as the voltage activated gates, only now it opens and closes by chemical means, and that's because these things here now this gap is full of these things, they get into one of these keyholes, that activates the same sort of pumping mechanism. And by the way, these things are also called ion pumps. They're referred to as that because that's what they do, they pump ions. This causes the voltage imbalance, okay, which then causes this process now. Okay, that starts this process, those chemically activated gates. Now, all of these, you know, there's a gazillion of them in there on a particular synaptic button, and you know, and I don't know if I mentioned that, but these are often called synaptic buttons, these things, because they do bulge out like that when you look at them under a microscope. That's what they look like. They look like synaptic buttons. Okay, now take a break here and then get back to it. But remember, this is a process by which informational signal is coming down here, an electrical signal is coming down here, and it's no current, but a field is moving. You have a field effect going on here, and it's pushing these things along, right? You know, like the bow wave of a field. Okay, it's pushing these along. It comes down here to the cleft. It joins, you know, it becomes part of the synaptic cleft, the presynaptic cleft, and it dumps all this material into the gap, which then these keys go down here and they open chemically activated gates, which are themselves ion pumps, which themselves set up a voltage difference, which then activates this process right here.